Okay, hello everyone in AMT 180. Here we are once again. I had to create another new link. For some reason, when I schedule a live meeting, I am not sure how to get it to open up. It just keeps saying waiting for AMT. So, again, like last time, I'm sure you guys will find your way here. I posted the newest link in the announcement on Canvas under lecture 9-3. I also posted the link in the chat. I don't know if anyone can even access that, but I am going to go ahead and start. Okay, so like we've been talking about, last time we had lecture, we ended on pressure sensing instruments. So today that's where we're going to pick up and continue. So this is a list of all of the pressure sensing instruments that we will discuss during the term of this course. Okay, so here we have engine oil pressure, manifold pressure, EPR stands for engine pressure ratio, fuel pressure, hydraulic pressure, vacuum pressure, and pressure switches. Okay, so we'll move on to, first we're going to discuss the engine oil pressure. So this comes directly from the Aviation Maintenance Handbook, the 8083 Volume 2. The most important instrument used by the pilot to perceive the health of an engine is the engine oil pressure gauge. And I think the majority of people will probably tell you that that's true. Engine oil pressure loss. A loss of pressurized oil to engine areas would rapidly cause excessive friction and over-temp conditions. This would certainly lead to catastrophic engine failure. We need that engine oil to lubricate all those very hot and metal parts of our engine in order for it to run effectively, efficiently, and correctly. This is a cool little video that I found. Some guy decided that he wanted to see how long it would take until his aircraft engine would be totally destroyed without oil pressure. So a fun little fact here. Oh, am I echoing?
It's not real silk. Stop marinating your man meat with unholy ingredients that are harmful.
Hey guys, what is up? John here from flyatmyhealth.com. Today we're answering a very important question. How long will the engine run for when you're out of oil? Okay, so we've already run up our engine. We've gotten it hot, 165 degrees on the oil temperature, about 330 some degrees on the cylinder head temps. So it is at operating temperature already. Then we went ahead and we disconnected the oil cooler line. So this line coming directly out of the engine where all that oil would normally flow to the oil cooler has been severed, so to speak, right? It's been disconnected and it comes down here to this valve. So we can keep the valve closed. Our engine is still going to have oil pressure when we first fire up. And we're going to have the oil be able to flow through this vinyl tube over to this bucket once we open up that valve over there. So what we're going to do is we're going to fire up, let it idle for about a minute or so, stabilize, get the temps back up, get the oil kind of flowing around there. And then we're going to open up that valve, and that's going to pump out all the oil. It's just as if you have severed an oil line. We're going to see how quickly you lose oil pressure. All right, so how long does it take for all the oil to pump out of the engine? We'll know that. And then once all the oil is pumped out of the engine, we'll see oil pressure drop inside the cockpit. And then we'll see how long this engine will run for after that before the entire engine seizes and is totally destroyed, in which case you would no longer, well, you'd be gliding, but you wouldn't be producing any power to go anywhere else. So how long do you have from the point of losing oil pressure to the point of a total engine failure? That is what we're going to find out right now. Good. All right, we got 92 degrees on the oil temp. We're going to go over to oil pressure, 67 psi. Let's go ahead and open up that valve and see how quickly this thing drains all of its oil out. We've got a little over 6 quarts in the sump right now, about 6.5 quarts, normal running. Oh, there goes the pressure. Needs to be down to 42. Oh, and we can see that thing is running out pretty quick. We're going to go ahead and increase RPM here and see how long we can keep this engine running. Oil pressure is 19, 18, 17, 15. Wow, it is dropping off there. 86. Well, not much in the way of oil pressure anymore. Look at good RPM. 4 pounds of pressure. Not really seeing any alarm here, right? We just see low oil pressure, but we don't see any sort of alarm flashing at us. We have no alarm anywhere in the cockpit warning us that, hey, you're out of oil. And it looks like that is really just pumping air right now. So I'm guessing that, yeah, the sump is totally out of oil. We're down to 1 pound of pressure. And you would probably be in big trouble right now. We can see we're slowly losing some RPM there, 2,100 RPM. And pretty stable there at 2,100. Maybe picking up a little bit of power here as our cylinders get a little warm again. Remember, we had pre-warmed up the cylinders, but things do cool down while it's sitting here. So we can see that maybe as the engines get a little warmer, it's starting to make more power, actually. We've got good fuel pressure there. Alternator is working beautifully. Almost out of gas. That's all right. So we can see just the tiniest bits of little gulps of oil being shot out of there. The last little bit's oil, but obviously 0 pounds of pressure here, 0 psi. No oil pressure. Oil temp has fallen pretty low here. 99, it's not really reading that accurately, obviously. Oil temperature is rising, though. Oil pressure is 0. Oil temperature is coming up. Remember, our oil temperature, initially we had warmed it up to about 165 degrees, but it did cool down between us getting out, getting all the cameras set up, and now. So oil temperature had come down a little bit, but we see it slowly coming up. I'm guessing whatever little bit of oil is left in that sump is probably a whole lot hotter than 101 degrees right now. This is full power, guys, all right? That's everything she's got. Now, obviously, our RPM is a little bit low here, 2,200 RPM, 2,250 at most. That's because we're just sitting here stationary. If we were in flight with full power, we'd probably be seeing somewhere around 2,600, 2,700 RPM. So the engine is making full power here, but we're just not seeing all of it here. We're not seeing the full RPM because, of course, we're stationary. Our static RPM, this is called our static RPM, and static RPM is a little bit lower than the RPM we see in flight. Now, what's interesting is the bucket of oil out there is actually starting to smoke quite substantially, meaning the last little bit of oil that's coming out of here, a lot hotter than 108. I've never seen oil smoking. It's actually coming out of this vinyl tube here, just really starting to smoke. Now, some RPM falling off here, 2,100 RPM. It's come down from about 2,200. Still set to full power, still set full ridge. Might try leaning her out here a little bit,
a little more heat, just like we might be in flight lean down just ever so slightly. Don't want to foul those spark plugs when we're trying to destroy an engine here, guys, right? I mean, we would hate to foul the plugs right now. So we can see oil temp 111, totally inaccurate from what it actually is, because that bucket of oil is smoking, and that bucket of oil doesn't have a heat source next to it. It is just the oil coming out of that final tube is super, super hot. The last little bits of oil being spewed out of this motor. And there we are, 2000, 1900. All right, here it is, starting to run really rough. We might potentially throw around, okay, there it is, 18, 17. Now we're got an engine failure, 1500. That's it, guys. This is going to be the end of it. Still 1500 RPM, still producing some thrust. Let's get her full rich. Let's give her everything she's got here. All right, 1300, 1350. Hang in there, buddy. Come on, you can do it. No oil pressure, 0. Oil temperature, 114. That's a total lie. We got a bucket of smoking oil there. This motor is not running so hot, but giving her everything she's got. And, yeah, pretty stable there at 1500. Something's happened because we've lost a lot of RPM, so we might have possibly stuck a valve at this point. May not have even really started to seize the engine, but we might have stuck a valve or something. The vibration's not quite as noticeable as sticking a valve. We'll talk more about sticking a valve here in a sec, what that might mean for us. We see about 1350, 1300, still producing some amount of power. This is still better than just gliding, all right, like a stone, okay? This is definitely some amount of power is being produced here, 1300 RPM, when we're not moving through the air at all. Is obviously some amount of power, probably a little over 100 pounds of thrust. Keep in mind that this airplane makes about 400 pounds of thrust at most ever. So still over 25% power is what you have available to you right now if you were in flight. This is shaking pretty good, though.
Play War Thunder now. Join millions of players across the globe in massive battles on tanks, aircraft.
Really shaking the air down to 1200 RPM. We're just going to let this guy run all the way in. We got full power set. Coming back to 1300. Actually gaining a little RPM there, 1350. Oh, starting to get better. 1500 almost. Something's making a little more power now. Oh, and here we are. We're coming back. We're coming back. We've got, wow, what do you know? If we weren't going to make the airport here, guys, maybe now we're gonna. It's all going to be all right. We just got a little burst of power there, almost up to 1800 RPM. And now it's coming back on us, starting to fail again. Still got good fuel pressure. I sure hope we don't run out of fuel before we burn up this engine. I did not count on the engine running for, better part of 7 minutes after losing oil pressure. But that's what it seems to be doing. Let's try to lean it out. Maybe we gave it a little too much fuel there. Come on, make some power. There we are. There we are. Making power. There we are. Make it to the airport. Come on. We're going to make it, guys. We're going to make it. Oh, my gosh. We're going to make it. The leg's being a little bit leaner there. Back up to 1900 RPM. Almost back up. I mean, that's over 75% power is what we're getting out of it now. Over 75% thrust.
So if you guys take absolutely nothing else away from this video, at least remember this. Whatever you do, don't freak out. There's a couple different things here. A, our engine's running for a very long time, all right? It's actually making enough power to not only maintain level flight, we could actually climb a little bit with the power that we were making. And we had several minutes of full power after losing oil pressure with nothing acting weird at all in the engine, all right? Now, not to say this is going to happen to you. You could have a different experience and your engine could fail a little bit quicker than this, but stay calm. That is the biggest thing here. You've got time, think, point your nose towards a good place to land, whether that's an airport or a good, safe, open area. Do not freak out, and remember that engines are a little finicky, especially when they're running without oil, so it may take some different things here. You'll see how we're playing with the mixture to get the best power out of the engine. We're possibly turning the fuel pump on and off, playing with the throttle a little bit. Maybe full throttle is actually not going to give you best power. Maybe reducing the throttle, closing the throttle plate a little bit helps. Keep an eye out for all those little fine details we do to get the most power out of this engine and make it last as long as possible to get us to somewhere where we would want to land rather than have to land.
All right, this might be it, guys. We're losing here. We're losing a little bit of RPM. Coming off 1800 down to 1700 RPM. Starting to shake pretty good. Try playing with the mixture and see if we can get any more power out of her. Oh, no, didn't like that. Let's go ahead and lean it out a little bit. There, she's coming back for us. 1500. For some reason, it likes being a little bit leaner here. Yeah, I think this might finally be it. Oh, there's 1,000. So we're just down to idle. We got full power set here still. Normal mixture setting. I don't know what else to do. Fuel pump on, guys. And we're down to probably about 30 pounds of thrust is all we're getting out of this thing. 40 pounds of thrust down here around the 7,800 RPM range. 138 degrees. 700 RPM. It feels like something's ready to snag and break in here. Really feels like something wants to break. Running pretty rough. Come on. All right, there, kind of death throws. Let's try reducing the throttle a little bit. See if that helps any. That actually picks it up a little bit. Yeah. Oh, there it is. You know what? It likes less power. It likes the throttle a little further close because that's just too much air for it to breathe at such low RPM. So as you start losing that RPM in flight, it's really coming back on you. Maybe reducing the throttle actually gives you more power there. Try to feed in the throttle a little bit. That helps. See if we can catch. We can catch and go a little higher. Oh no, that's trying to shut her down. Throttle back to where it was. Come on.
Okay, so it turns out not all laptops are created equal.
Oh, that's really, really rough. Wow, really rough. Okay. Yep, this would be really scary. And come on, a little bit more. Give me some more there. It's still running. It doesn't like to run full throttle. That really makes it want to shut off. Oh, come on, catch. It likes a little bit less, maybe half throttle. It's giving me about 1,200 RPM, but shaking like crazy. Really shaking. Obviously, in flight, I think I probably would have voluntarily shut it down by now because I'd be afraid of something really going wrong. Wow, it's shaking. Come on. Oh, it feels like one cylinder is running. Oh, and we're coming back. We're coming back here, guys. And we're coming back. A little bit of throttle out actually helped. Bringing that throttle out. Now try to slowly advance that throttle, get a little more power. Oh, it's really, really finicky. Oh, that's all she's got. Let's see what the temps are.
Okay, so that is it. That is, almost 20 minutes of this thing running from the time it lost oil pressure. So by the time all the oil was out of the engine, almost 20 minutes until this engine actually stopped making any power. Now, it produced almost full power for several minutes and then really started giving us some problems. So I want to go ahead, moment of truth, turn this prop through by hand here. It's a little stiff, as you can imagine, but I want to check all 4 cylinders. There's 1, 2, 3. No compression, really, just friction. And, that's number 4. Okay, there we go. 4, all 4 cylinders. It's good as new, guys. It's a freshly overhauled engine. It's a little tight, needs to be broken in, no worries. I got a feeling this thing's gonna run again, with not much effort, actually. But you guys will find out on fly@mikealpha.com, because we're gonna post that video up on the website at fly@mikealpha, whether or not this thing ever does run again. We're just gonna let it cool down a bit. We were seeing engine temperatures, cylinder head temps over 500 degrees. When we're really measuring it properly, getting in there, over 500 degrees on the cylinder head temps. Oil temps, well in excess of 200. Obviously, not a really good way to measure it effectively, but oil temps well in excess of 200. Ultimately, I don't think I'm going to lose as much sleep at night anymore over all those students I flew with. And of course, we always talk about what happens if you lose oil pressure. And I always told them, well, you got to find a place to land real soon. But I guess I'm not too worried because it seems like they're going to have a lot of time to find a place to land. If this happens to you somewhere in Florida, well, I can't say it's going to be this positive of an outcome, right? All right. So if this happens in flight, I don't know, it could seize the engine. You could have a total engine failure within seconds. But it took us 20 minutes. I'm guessing most other 0320s are going to be similar, right? 30 seconds, a minute, a couple minutes, 20 minutes, 30 minutes even. But yeah, took us about 20 minutes. All of our oil is right here. This is about 7 quarts of oil sitting here in this 5-gallon bucket here. And yeah, it's toasty. It's pretty toasty. Really, other fascinating things we learned, I didn't see it from inside the cockpit, but cameraman saw it. And this happened, he said, about 10 minutes. something just spat out of the exhaust. So yeah, somewhere 10 minutes into this whole deal, something spit out of the exhaust and kind of burned the pavement. So that is it. That is really what's left of our engine. But you know, we're gonna let it cool down, pour a little water on it, see if just steam clean it a little bit. Steam cleaning does wonders for engines, you know. Not really, don't actually do that on your own engine. But we're gonna let this girl cool down a little bit, try to fire her back up here. My guess is, I think it's gonna go pretty well, but if you really want to find out what it takes to get this thing running again, well, check it out on flyatmikehealth.com. Lots more videos like this on flyatmikehealth.com. An entire series of what is inside of an airplane / let's destroy an airplane video series, right? So obviously everyone out there wants to know exactly how long their engine is going to last when they lose oil pressure. Go ahead and share this video around. Not saying that this is how long yours is going to last. Hopefully it lasts this long if it never happens to you. Hopefully it never happens to you in the first place. And yeah, not a whole heck of a lot of time there when you actually open up that valve. If you had an oil line sever in flight, what would you say, about 20 seconds or so until you are, well, really out of oil pressure and you're on the road to this destruction. So share it around, guys. Make sure you like the video, subscribe if you guys have not already. Make sure you follow the...
Okay, so that is an overview of some things that can happen when losing oil pressure. Not that I want you guys to go out there and run anybody's engine out to 0 oil pressure. But an interesting experiment, I thought. Not too often that we see people get to experiment that. So oil pressure is extremely important to your aircraft and to your engine. Like I said at the beginning of the slides, you know, probably the most important instrument to the life of your engine. Okay, so thank you, Robert, for the feedback about the red text. I did change that, and I'm glad you said something because I had other slides that had some red text in there just for the engine gauge markings. So I went ahead and changed those as well. So there's that slide again for anybody else that possibly couldn't see it. The most important instrument used by the pilot to perceive the health of an engine is the engine oil pressure gauge. Okay, we talked about the loss of engine oil pressure. So a little bit about the gauge. The engine oil pressure gauge can be displayed on digital or analog instruments. And it is measured in PSI, which I'm sure we all know what PSI means, pounds of force per square inch. So engine oil pressure, a gauge that's a digital instrument system, they use a sensing unit that sends output to a computer. From there, the oil pressure values are displayed on the aircraft's cockpit display screen. Analog instruments that are engine oil pressure gauges often use direct reading board-on-tube oil pressure gauges to read and display oil pressure. Remember when we talked about board-on-tubes and diaphragms and bellows in the last lecture? So I hope you do, because that is what we're talking about when we talk about analog engine oil pressure gauges. So I'm not sure if the green and the yellow text is any better to see. Well, I can view it on my computer. I guess it's a little better than the red. But this is a picture. It might be a little blurry for you guys. This is an example of an engine oil pressure gauge. Oops. Okay, so when you guys do get the slides, you can see this a little better. But we have the markings on the pressure gauge. So this pressure gauge actually, if it's too blurry for you, I'm going to kind of explain this a little bit. This pressure gauge has these 2 semicircles right here, and this is your the markings area. And so on this side, it says press, P-R-E-S-S, so standing for pressure. And on this side, it says temp, standing for your engine oil temperature. We are going to go over engine oil temperature at a later time in the course. probably maybe sometime next week, but today I just want to focus on the engine oil pressure. Okay, so this is a dual gauge. It's going to tell you your pressure and your temperature for your engine oil. Right now, I'm just talking about your engine oil pressure. So we have this little semicircle reading panel here, and it has a list of numbers from 0 all the way up to 115. So I just want you guys to be familiar with these colors and what they mean to you on this gauge. So the green right here, I marked in green, is our normal operating range. And in this semicircle area, you'll see there's a small strip of area that's marked green. So that's your normal operating range for your engine oil pressure. We also have 2 lines that are red. So we have a line at the very top. Up here, it's marked at the 115. And over here at the bottom side, it's marked at the number 20. So these 2 red lines are your max and min lines, maximum and minimum oil pressure. You don't want to exceed them or go below them because it can cause damage to your engine. And then there's also a yellow portion toward the top of your instrument by the top red line. So when you are getting up to this temperature, you have this little yellow area, and naturally that's going to stand for like, hey, caution, it's getting too hot. You don't want to go any further. You know, just like your car, if you're overheating your car, you can overheat your engine. So there's this yellow area, and that's a caution area where you should be like kind of trying to figure something out if you're in that area. Okay, so that's what those markings mean to us on an engine oil pressure gauge. This is actually a pretty good picture too, when you guys can see it in the slides. It labels your maximum and minimum areas for your oil pressure, and then also your normal operating range. Okay, green and yellow text is a little bit better. That's good to know. These are just some examples of different engine oil pressure gauges that you guys will see in many different aircraft. There is a variety of gauges that are out there. So we need to know how to read them all, you know, and there's minor differences between them. We have this one over here on the left. It says oil pressure PSI goes from 0 to 150, and it has this small operating range right here that's just marked with the green. You also have your max and min red lines here. So no caution area, but you know, pilots that are familiar with these things, they know those numbers. And same with us, we need to know that these numbers are correct. And what we would do with any gauges is if a marking is not legible, we need to know where that marking should be and that it's legible for the pilots flying these planes. So if that isn't legible, we need to know to annotate that and get that corrected or changed. So you also have 2 of these oil pressure gauges here that you may see. The whole thing has some kind of color code system. So it goes from 0 to 10. So it's using a different format of the numbering system of how to read it, okay? So we still have our red areas. They're marked out in a little bit of a bigger area. So we have our minimum and our maximum limits that we don't want to go below or above. We also, in this one, have the caution area. We have our yellow on both sides, and we have our normal operating range that we optimally want to stay in. And then we also have this version over here where it is also a dual gauge. So you have this version has the temperature on the right and the pressure on the left, both reading for oil. So gauges like this that are a dual gauge, you're always going to see, what it's measuring somewhere. So it has this label oil, and then it's going to say pressure or temperature. They also do that for fuel. They can do pressure and quantity. They can do dual instruments like that. Okay, so this one doesn't even have any green, yellow, or red markings. So that's something that's annotated in the manual or the pilot's operating book, then they know what those ranges should be. So this is a much older version of these analog instruments. So you will often see something marked with, I see this one a lot with just the green. And then newer aircraft, you know, there's also digital versions of these that have all kinds of colors. And more. There's even more styles of oil pressure gauges, okay? So we have this one here that similarly has just the green marking for our operating range. We have our minimum and maximum, and then it goes all the way up to 300. We also have this one that just has a yellow and a green operating range. It goes up to 130, measures in PSI. Actually, this one over here is oil temp measured in degrees. So, which we'll get into later. And then another dual gauge. I've seen these ones, and I think they're kind of cool because like the needles, I think they're kind of cool. It's kind of like a butterfly. Okay, so this one again doesn't have any green, red, or yellow markings, but you'll have temperature on one side, pressure on one side, and these needles kind of work opposite of each other. They're positioned right here, but because they're on the opposite sides, they will tell you your pressure. So like this one, when the aircraft is turned on, this one will read, you know, the temperature and your oil pressure range. So again, a pilot or a maintainer needs to know what those ranges are so that they're in, when you're running up engines to check, you know, do ops checks or functional checks for any components that we've changed or any type of stuff like that. You need to know the operating ranges of these things so that you know if you have an over temp condition or maybe your engine oil isn't building any pressure, because that could be a big problem. And then another one over here, an older version, you know, just basically goes 0 to 100 PSI. And it's, again, you need to know what that operating range is. Okay, so manifold pressure. We're gonna go over the manifold pressure gauge. And we will talk about some of the factors of that, some of the markings on the manifold pressure gauge. So here, manifold pressure, the manifold pressure gauge measures the pressure of the air in the engine's induction manifold, okay? So I want you guys to be familiar with these two sentences because you are going to see them both. But what manifold pressure actually measures, the manifold pressure gauge, actually measures the lack of pressure or the vacuum or the suction in the engine manifold intake, okay? So, and that's something that you should know as a AMT, as a maintainer. You should know that, okay, this manifold pressure gauge, it does read pressure, but it's actually programmed to read the lack or the suction pressure of that manifold intake. Okay, so there's a big difference between, you know, in the engine oil pressure gauge, we're reading the build of the pressure building up. In our manifold pressure gauge, we are reading how that pressure becomes a suction once, you know, we take off in the aircraft. Manifold pressure gauge, this indicator is specific to reciprocating aircraft only. You don't need a manifold pressure gauge in turbine aircraft. They're called something else because the intake air is used in a different manner, not so much in an induction system. Okay, so we will have manifold pressure gauge on reciprocating aircraft. On turbine aircraft, you'll usually see a turbine inlet gauge, some type of intake air gauge, and we will also cover those in a later lecture, the turbine instruments. Okay, so in a manifold pressure gauge, the lower the pressure is, the higher the induction, or the higher the induction on the manifold gauge. Okay, so the lower the pressure, the higher the reading is going to be on the manifold gauge. Okay, this information, these next few slides come from a military manual. And so sometimes in the military, you will see a blue range marking. Now, I haven't seen it so much in civilian aviation, but these are some good things to know, the differences between these range markings and the gauges that you will see. So manifold pressure gauge markings. Our manifold pressure gauge on this one has a blue arc. And the blue means that the range within which operation is permitted in auto lean, that's an auto lean condition. The bottom of this arc indicates the minimum manifold pressure desirable in flight determined by engine characteristics. The top of this arc indicates the manifold pressure at which mixture control must be moved into auto rich. Okay, so what that's saying is in this blue range, if we are toward the top of this blue range, toward the this side, toward the higher end of this blue range, then that would indicate that the manifold pressure mixture control needs to begin to be moved into an auto-rich condition. Okay, so this is all stuff that you would learn more, like such as changing the fuel mixture condition, stuff like that. That stuff is really more explained in the carburetors class. But I just want you guys to be familiar with all of these markings that you could possibly see on these different gauges. Okay, same gauge. So this is like I said, a military gauge. So same gauge. Might be a little blurry. Oh, I see somebody says I cannot see the highlighted word. Oh, okay. Yeah, these texts are this particular text in these next couple of slides are like they wrote in this like white border for some reason. So what I can do is I will copy and paste these into the chat. Give me just a minute. I'm going to do that so you guys can follow along. Okay, so I just typed in the chat this slide that I just reviewed. So in the chat, I wrote what this blue range marking means. That's specific to this dial over here. The dial on the slide. Okay, so it has this blue range marking. And that blue arc indicates the range within which operation is permitted in auto lean condition. Okay, so this blue range is only used for when you want to operate in an auto lean condition in a reciprocating aircraft. Okay, but if you get toward the bottom of this blue arc, that indicates that it's the minimum manifold pressure desired in flight. Okay, so in auto lean condition, if you're toward the bottom end of that blue arc, that's the minimum. That's your minimum to operate in an auto lean condition. And then in the same slide, it explains getting toward the top of that blue arc If you're at the top of that blue arc, it indicates that the manifold pressure at which the mixture control must be moved into auto-rich. Okay, so if you get toward the high end of this blue arc, you want to start moving your mixture into auto-rich. And then the low end of this blue arc, you want to move into auto-lean. Okay, so this obviously isn't a pilot class, but we do need to know what these markings mean. If you show up to work on an aircraft and it has a blue range marking, you need to know, oh, okay, that is for when manifold pressure is operating in a certain fuel mixture. Okay, so I'll move on to the next slide, and I will also paste. Whoops. I will also paste it because these 3 slides have that same highlighted kind of wording. Okay, so this next slide is showing you the green operating range of these markings. Okay, the green line or the arc in this instrument. Okay, so we see that on the other side of the blue arc. So what that says, what the slide says, is that green line or arc describes the range within which operation must be an auto-rich. Okay, so these are the markings for an auto-rich condition. The radial or top of this arc indicates maximum continuous power. All operation above this manifold pressure is limited in time, usually 5 or 15 minutes. Okay, so these are going to be your maximum and minimum guidelines for a certain set of fuel mixture conditions. Okay, so keep that in mind because we want to know what these things mean when we see an instrument. And I'm going to put this last one in the chat as well. Okay, so I entered the information for this next slide in the chat as well. Okay, so here you see this red line. Okay, this red line sticking out from the instrument. So what that red line means is it indicates manifold pressure for takeoff, and typically manifold pressure for takeoff should be at whatever it is for atmospheric pressure is usually what it should read or what it's going to read. Okay, so in that specific instrument, which I said this one came from a military maintenance manual. I just want you guys to know that these instruments are out there. They're out there with the blue and the red line and the green, and if you come across it, you need to be familiar with the fact that this stands for something. Okay, it stands for when you're operating in certain conditions. Okay, so here's another manifold pressure gauge, one that people are probably a little more familiar with. It's similar to the, at least the markings are similar to the engine oil pressure gauge. We have this large green marking area. We also have a small yellow marked area, and we have our red line, which means in a manifold pressure gauge, that means what the pressure should be at takeoff, okay? So don't get it mixed up with the engine oil pressure gauge where we have a max and a min that our engine oil pressure should not exceed or fall below. The red line for the manifold pressure gauge is what we should be at for our takeoff. And then green range, normal operating range on this particular type of instrument. And yellow, caution area when in flight. We should be a little bit worried if we get in that area, because that would mean that the manifold pressure, again, manifold pressure meaning the suction is not where it's supposed to be, or it's not holding suction, and there could be something wrong. This is also a good picture as it refers to a manifold pressure gauge. Okay, so we have our manifold pressure gauge. In this particular gauge, it just has the green area and your red line where you want to be for takeoff. So the pointer should be somewhere in that area for takeoff. And then our normal operating range conditions. What this other side of the picture shows is how this instrument works behind the faceplate, okay? So it has some good labels that you guys will probably be able to see once you get the slides. But we have, right here, we have an aneroid, okay? So we talked about that in my last lecture. So this is like a diaphragm, and it has a certain altitude compensating, that's the altitude compensating device. And this says up here, okay? So I just want you guys, I'm not gonna ask you guys what the labels of these are today in your quiz, because I knew that you guys probably wouldn't be able to see it very well. So when you get the slides, you can see it a little better. But here we have our diaphragm type of pressure sensing device here. It also shows you how this pinion gear is connected to the needle that will move, your needle marker when it's being read. And right here it says capillary assembly. This is where your air is connected to, so it can read that manifold pressure reading. So that is a really good diagram about how the internal components of this instrument works. These are some more examples of manifold pressure gauges. We have this one that we discussed that's been in a couple of slides. We also have this one that doesn't have any, green, yellow, or red or blue markings. So again, you would, want to know what that pressure needs to be, what it needs to be at takeoff, what the good operating range is, so that when you are ops checking aircraft, you can tell, hey, the manifold pressure is reading correctly, or hey, it's way out of line, and that's a big problem. This is also another manifold pressure that you could see, and you probably can't see it there on the screen there, but it has some areas in here that are marked in blue. Okay, so now we know what that means, and it again doesn't have any like red, yellow, or green type of arcs in here. So we would need to know what those parameters are. Not that you guys don't need to know them, like you don't need to memorize them, but out in real life in the field, you're going to need to know where to find them in the book prior to doing any engine run-ups, because that's part of the checklist for an engine run-up is notating what the manifold pressure is, at least for in reciprocating engines. Okay, so manifold pressure gauge. This gives us an indication of power being developed by the engine. The higher the pressure of the fuel-air mixture going into the engine, the more power it can produce. This is also a good diagram, and this shows some of the differences between a manifold pressure gauge and some gauges that you'll see for a turbine aircraft. So over here we have our manifold pressure, just like we've been talking about, and we will discuss turbine aircraft indicators in a later lecture. Today we're focusing on manifold pressure, but I want to introduce you guys to the fact that there are some different instruments when it comes to turbine and reciprocating aircraft. Okay, so I want you guys to type in the chat since I'm kind of able to get more familiar with it now. Over here on our manifold pressure gauge, which is this one on this side if you can't read it, we have a yellow marking, a yellow arc, and we also have this red line here. What's that red line for? Go ahead and type in the chat if you're able. Yes, pressure for takeoff. Good. It was actually the last thing I entered in the chat anyway, so probably pretty easy. Okay, what about the red lines on the oil pressure gauge? What do those mean? There's two of them. Good, yeah, max and min. So the red lines on your oil pressure gauge are going to stand for your max and min pressure. Yeah, remember we're talking about the oil pressure gauge. So on the two red lines on the oil pressure gauge are going to stand for our max and min pressure. We will go over the oil temperature gauge in a different lecture. Okay, so on this side, good job with those responses. I mean, there's only a couple of you. I don't know how many people are actually on this lecture, but there is so these two gauges over here on this side of the chart. We have one gauge says torque, one gauge says turb out, and we have torque percent and turb out temperature. So turbine out temperature, there is a sensor that can read the turbine outlet temperature. Okay, so these are some, and then we have our torque reading in percentage. Okay, and this says left panel shows torque and turbine outlet temperature gauges commonly used with turbine powered aircraft. Right panel, meaning this side, the manifold. Right panel shows a manifold pressure gauge is commonly used with piston powered aircraft. Okay, so you guys don't need to know anything about these turbine instruments in too much detail right now because, but I just want you guys to know that there are different instruments for turbine and reciprocating aircraft. Different ways to read how that air is coming in and pressurizing in those different types of engines. Okay, so I have two videos here. This one is on the manifold pressure gauge. I think it's a good video. It kind of has a good description of the manifold pressure gauge. And then we will also look at a video of the aircraft engine instruments, meaning all of the instruments, which is kind of a foreshadowing into what we will continue talking about in further lectures. Okay, so we're going to start with this manifold pressure video. This video is all, it doesn't, nobody's talking in the video. It just has music, and it has some like text on the screen. So we'll see how well it's able to be viewed. Okay, so if you could not read that, I can view it on my screen and it seems pretty legible. Then please go back and review it tomorrow when the slides are available. There's nothing specific in your quiz today that was not shown on the lectures that you would miss from not viewing that video. So it's just a good explanation as well of your manifold pressure gauge and how it works. Okay, so this next video, whoops, is my last slide for today. And it is going to talk about
Hey guys,
engine.
what's up? John here from fly8myalpha.com, and today we're going to cover in the shortest and simplest way possible what a constant.
And it shows, how do I get out of this? It shows the aircraft engine instruments and has a little brief description about all of them.
Why modern light aircraft safely without it?
Hang on, for some reason I have like two videos going here, so let me see what's going on. Okay, let's try that again.
Is long and service, and faulty operation will be commonplace. It's thus essential that engine instruments are fitted to aircraft and that they function correctly. It would be very difficult to fly a modern light aircraft safely without its engine instruments. Some engine instruments are what are termed engine condition indicators. These include the oil pressure and oil temperature gauges and the exhaust gas temperature gauge. They literally show the actual condition of the engine. Other engine instruments are called performance indicators. Within this group are placed the engine RPM gauge and the manifold pressure gauge. They are intended to show how well the engine is performing. Furthermore, without engine instruments, effective management of the engine would be impossible. The engine would not give long and efficient service, and faulty operation would be commonplace. It's thus essential that engine instruments be fitted to aircraft and that they function correctly. The pilot must also be assiduous in monitoring the engine instruments. Piston engines are heat engines. The power they produce is directly proportional to the heat released during the combustion of the fuel. Engine components and systems are designed to withstand certain temperatures. If the temperature limits are exceeded, the components may fail. To allow safe operation, the engine temperatures must be monitored. The following temperatures are monitored in piston engines: oil, exhaust gas, and cylinder head. Monitoring the engine oil temperature is important from at least 2 points of view. Firstly, the oil itself will only retain its lubricating properties up to a certain maximum temperature. Above that temperature, the oil breaks down and the moving parts of the engine begin rubbing against each other and getting even hotter. Engine failure quickly follows. Secondly, the engine expends a percentage of its power forcing the oil into the bearings. The colder the oil, the larger that percentage of what is essentially wasted power will be. If the aircraft is to perform safely, the engine oil temperature must reach a certain level before the pilot can be sure that his engine is delivering the power to the propeller that the manufacturers intended. Oil temperature is normally sensed where the oil enters the engine, after it has exited the oil cooler. In a typical engine oil temperature indicating system, the indicator is powered by the aircraft electrical system. An electrical resistant type thermo bulb installed in the engine oil pump housing measures the temperature of the oil entering that unit. The temperature reading is transmitted to the indicator, usually in degrees Celsius. An exhaust gas temperature gauge can show you whether your engine combustion chamber is running too hot or too cold, too lean or too rich. An exhaust gas temperature probe is installed about 4 inches from the cylinder head on the exhaust system. The probe is the junction of 2 dissimilar metals. This is called a thermocouple. When the thermocouple is heated, a voltage is produced, which is proportional to the temperature at the junction. The gauge is a millivoltmeter, which is calibrated in degrees Celsius or Fahrenheit. Although the exhaust gas temperature gauge can help in troubleshooting a problem on the engine, it's primarily a fuel management instrument. The cylinder head temperature gauge is an engine instrument designed to protect the engine against its enemy, excessive heat. The principle of operation of the cylinder head temperature gauge system is similar to that of the exhaust gas temperature gauge. A probe is mounted on the engine cylinder head, and this sends a voltage to the gauge in the cockpit, which is proportional to the temperature. Most general aviation engines sample the cylinder head temperature of the hottest cylinder. The hottest cylinder is determined by extensive flight tests carried out by the engine manufacturers. The function of many aircraft engine systems relies on liquids and gases whose pressure must be measured and indicated. The gauges and indicating systems fall into 2 categories: direct reading and remote indicating. Direct reading describes the type of instrument used when the fluid that is being sampled is fed directly to the interior of the instrument positioned in the cockpit. Remote indicating is where a separate sensing element is connected to a pressure source at some remote point, and the information required is transmitted electrically to the instrument in the cockpit. Pressure is defined as force per unit area. In engine instrument terms, it's normally indicated in either pounds per square inch or inches of mercury. In connection with engine pressure measurement, we are concerned with the following terms: absolute pressure and gauge pressure. Most pressure gauges measure the difference between the absolute pressure and the atmospheric pressure. To actually measure pressure in a system, elastic pressure sensing elements are used in which forces can be produced by applied pressures and converted to mechanical movement. The movement can then operate a direct reading gauge or an electrical transmitter. The sensing elements commonly used are diaphragms, capsules, bellows, and Bourdon tubes. Diaphragms consist of corrugated circular metal discs, which are secured at their edge, and when pressure is applied, they are deflected, as shown here. Diaphragms are used to measure relatively low pressures. Capsules are made up of 2 diaphragms placed together and joined at their edges. The device thus constructed can then be used to either form a sealed chamber, which is called an aneroid capsule, or a chamber which is communicated to a pressure source, which is called a pressure capsule. Capsules, as diaphragms, are also used to measure low pressure. but capsules are more sensitive to small pressure changes than are diaphragms. The bellows type element can be considered as an extension of the corrugated diaphragm principle. It may be used for high, low, or differential pressure measurement. The Borden tube is about the oldest of the pressure sensing methods. The element is essentially a length of metal tube which has an elliptical cross-section. The tube is shaped to represent the letter C. One end of the tube is sealed. This is called the free end. The other end is connected to the pressure source and fixed so that it cannot move in relation to the instrument base. When pressure is applied to the tube, it tries to straighten. This movement is magnified by levers and used to drive an indicator pointer. The Borden tube can be manufactured to indicate high or low pressure, but it is normally associated with higher pressures, such as engine oil pressure. Oil pressure is sensed at the outlet of the oil pressure pump. Normally, the oil pressure of an engine is maintained constant by an oil pressure relief valve. There are, however, situations which may affect the engine or the oil to the extent that it is beyond the ability of the pressure relief valve to maintain the oil pressure within the prescribed limits. It's at these times that the oil pressure gauge, if it's used in conjunction with the oil temperature gauge, can indicate to the pilot the best course of action to retrieve the situation. The manifold absolute pressure gauge of a piston engine uses two bellows to measure both ambient atmospheric pressure and the pressure in the inlet manifold. Note that this gauge measures absolute pressure and is calibrated in inches of mercury. When the engine is running, this gauge may indicate less than atmospheric pressure. Earlier versions of this gauge were calibrated to read boost in pounds per square inch and called boost pressure gauges. When the engine is not running, both types of gauge, the manifold absolute pressure gauge and the boost gauge, will read ambient atmospheric pressure. While the aircraft is stationary on the ground, this particular indication is called static boost. A fuel pressure gauge may be fitted to fuel injection fuel systems and can be used to indicate metered fuel pressure. In some cases, by calibrating it in a suitable manner, the fuel pressure gauge can enable the pilot to adjust the air-fuel mixture to suit the aircraft's altitude and the engine power setting. The measurement of the quantity of fuel in the tanks of an aircraft fuel system is an essential requirement. The simplest form of volume indication is a float system. Early aircraft had a float which sat on top of the surface of the fuel. Attached to the float was a piece of wire that protruded out of the top of the fuel tank. As the fuel level reduced, so the wire disappeared from view. There have been many variations of this system. On light aircraft, the most common of these uses a float which moves to position a wiper on a variable resistor. This in turn alters the current flowing to an indicator, moving a pointer over a scale calibrated in volume. The disadvantage of this system is that the indication is not linear, and there is no provision for making adjustments for system accuracy. The gauge is set to be accurate at the low and empty positions. The system is also subject to errors whenever the aircraft maneuvers and the attitude changes. As well as the quantity of fuel measured, the rate of fuel flow can be shown. The fuel flow meter can display volume flow or mass flow. A simple flow meter can be an adaptation of a pressure gauge. This system is used on many light aircraft piston engine and fuel injection systems. The measurement of engine speed is of vital importance, since together with other parameters, accurate control and monitoring of the engine can be achieved. On piston engines, it's crankshaft speed that is measured. The The RPM indicator is called a tachometer, or tacho for short. The basic method of measuring engine rotational speed on piston engines is the mechanical magnetic tachometer. The mechanical tachometer consists of a flexible drive shaft and the tacho indicator. One end of the flexible drive shaft is connected to the tacho indicator in the cockpit. The other end goes to the accessory drive casing on the engine, where it's driven through gears from the crankshaft. The input drive causes a magnet to rotate. The magnet rotates inside a copper or aluminium drag cup. This induces eddy currents in the aluminium drag cup. Eddy currents are caused by the magnetic field of the moving magnet acting on the electrons of any metal in the vicinity of the magnet. The eddy currents themselves generate a magnetic field which interacts with the magnetic field of the magnet. This interaction causes a torque, or turning moment, which is established to turn the drag cup in the same direction as the permanent magnet. A shaft extends from the drag cup and is connected to a pointer. The turning motion of the pointer is against the tension of a hairspring, which controls the drag cup position and hence the position of the pointer. The flexible drive is driven at reduced speed, but true speed will be shown on the indicator. The indicator incorporates compensation devices for changes in temperature. Left-click on the blue slider button situated below the tacho generator diagram with your mouse, and move it right and left to see how the device works. Notice how the spring restricts the drag cup as it turns the pointer.
Okay, that is a little introduction to some more of the instruments that we will
The
review.
pedostatic system.
And that concludes lecture for tonight, or September 3rd. Don't forget to take the lecture quiz by midnight tonight. It's posted now. I think it's available in about 10 minutes, but I will see you guys in lab very soon.